In this video, we'll be discussing the tools, materials, and hand soldering techniques that are used to attach through-hole components onto printed circuit boards, using both tin lead and lead-free solder. Although most of the electronics assembly industry has switched to lead-free solder alloys, there are still high reliability applications that require the use of tin lead solder. Let's begin by looking at a hand soldering workstation. Your workstation and the area around it should always be kept clean, well lit, and uncluttered. Any dirt, grease, solder splatter, insulation cuttings, and other debris should be cleaned away often, since they can contaminate the assemblies you'll be working on. It's a good idea to use ESD-compliant wipes or a brush to do this to avoid injury. Eating or drinking at your workstation is not permitted, because the oils or residues from the food or beverage can contaminate the assembly. Additionally, certain types of hand creams or skin lotions can also contaminate component leads, lands, and solder joints. Eating at your workstation can also cause health problems. The solder wire you'll be using may contain lead, which is poisonous if ingested. Lead from the solder can transfer onto your hands and then onto any food you eat. Please review all applicable material safety data sheets and wash your hands before you eat or drink anything, or even after handling any solder alloy, regardless of the composition. Another safety issue is the fumes given off during the hand soldering process. Some people are allergic to the flux fumes that are released when the solder is melted. A fume extractor can help remove these vapors. We'll be talking more about flux composition a little later. Another concern to be aware of is electrostatic discharge, or ESD. ESD can occur when static electricity from your body is discharged into an electronic component. This static zap can overload and degrade or destroy the microscopic circuitry of certain types of components. IPC has a detailed training program for ESD prevention. Now let's discuss soldering irons. Today, almost all production soldering is done with controlled output irons. Controlled output irons will maintain the selected tip temperature during soldering operations, no matter what the load is. Some controlled output irons operate at a specific temperature that is preset by the manufacturer. Others are temperature variable, using an analog or digital control. Temperature selection needs to be based on the solder alloy used, what component is being soldered, and the thermal mass of the circuit board. In general, a tip temperature of 315 degrees C or about 600 degrees F is a good starting point for soldering with a tin lead alloy. For lead-free alloys, a good starting point is 350 degrees C or 662 degrees F. Variations in the alloy, either tin lead or lead-free, will require variations to the starting point temperatures. Selecting a soldering iron tip of the proper shape and size is also very important. The amount of heat that is transferred to the parts being soldered depends not only on the temperature of the tip, but also how much of the tip touches the parts being connected. Pointed tips, such as the conical tip, are used to transfer heat into a small area. These tips should be used with small lands and components that need very little solder and have minimum thermal mass. A chisel tip will transfer more heat because more of the tip will contact the parts to be soldered. As a general guideline, the width of the tip should be slightly less than the diameter of the land that's being soldered. Every solder connection should be completed in the shortest possible time to prevent excess heat from spreading to nearby areas of the board and causing thermal damage. 3 seconds should be the average time, or dwell time, to complete a hand-soldered joint. If it takes more time than that, you may be causing heat damage to the board or the component. Heat damage can sometimes be visible on the surface of the board. It can also exist on inner layers, where it can appear as isolated white spots called measles. Measles are not a cause for rejection. Heat damage can cause internal delamination of the base material. Internal delamination is where two layers separate, creating a void. If there happens to be any internal conductors within this delaminated area, there will be little or no electrical insulation between them. In high humidity environments, delamination can result in electrical problems. Excess heat can also separate or lift the land from the base material. This is a microscopic cross-section of a plated through hole that has been damaged by excessive heat. When this area was overheated, different expansion rates for the metal and the base material caused this crack in the plating. Barrel cracks can prevent the electronic signal from traveling through the hole and result in signal failure. This particular problem would not be visible during final inspection, but it will cause reliability problems in the end product, including intermittent faults which may pass final testing. As you can see, heat transfer may be the most critical issue in hand soldering, and there are quite a number of factors that can affect it, including the wattage or power of the soldering iron, the amount of time the iron takes to make up for any heat that is lost in the soldering process, the size and shape of the soldering tip, and the amount of time the connection is contacted. All of these variables will be determined by the type and size of the connections you'll be soldering. You'll learn how to make the right decisions from the information in this video and by experience as you perfect your soldering skills. Depending on the soldering application, you'll be using either tin lead or lead-free solder. Let's examine the characteristics of these types of solder. We'll start with tin lead. The most common tin lead alloys used in the industry today are 60-40, or 60% tin and 40% lead, and 63-37, or 63% tin and 37% lead. Both alloys begin to melt at 183 degrees C or 361 degrees F. However, the temperature that the alloy actually melts is determined by the ratio of tin to lead. 60-40 solder begins to melt at 183 degrees C, but does not become fully liquidous until it reaches 190 degrees C or 374 degrees F. This 7 degrees C difference is called the plastic phase and is extremely critical during the heating and cooling of the solder joint. Movement during the plastic phase can cause a disturbed or fractured joint. Disturbed or fractured joints may be unreliable. 63-37 solder, however, has no plastic phase. It melts and cools completely at 183 degrees C and is known as eutectic solder. Because of this, and because it also quickly solidifies, 63-37 solder is commonly used. The amount of time solder takes to solidify can also affect the strength of the solder joint. While the solder joint is cooling and the solder is not yet solidified, any bump or vibration can break, loosen, or otherwise damage the electrical and physical properties of the solder connection. Again, the result is called a disturbed solder joint. If the solder appears wrinkled or distressed, this indicates a mechanical weakness, which can eventually cause electrical failure. Now, let's turn our attention to lead-free solder. There are many different types of lead-free solders available today, so it's important to note that they will all have different melting points. The most common lead-free alloy for hand soldering applications consists of tin, silver, copper. One common tin-silver-copper alloy is called SAC 305 and contains 96.5% tin, or SN, 3% silver, or AG, and 0.5% copper, or Cu. SAC 305 begins to melt at about 217 degrees C, or about 422 degrees F, which is 34 degrees C higher than tin lead. SAC 305 solder has a plastic phase of about 3 degrees C, or 6 degrees F. Your company will select the specific lead-free soldering alloy you will use for hand soldering applications. Lead-free solder alloys tend to have a stronger surface tension, meaning they are more difficult to spread along the surface of the connection than tin lead alloys. Here are some other things to be aware of when using lead-free solder. Components and circuit boards need to be able to withstand potentially higher soldering temperatures. Solder defects may increase due to poor wetting and may create more rework. Fluxes will need to clean surfaces more aggressively and will need to function properly at higher temperatures. That's because there's more possibility of oxidation and potentially longer soldering times because of the higher melting temperature. The more active fluxes, in turn, may also require a more thorough cleaning process to remove the more aggressive flux residues. Finally, the solder joints may have a different appearance depending on the lead-free alloy used. The appearance of the connection may be visually disturbing to inspectors, but solder joint graininess has never been a problem or a reliability issue. Just because it looks different doesn't make it bad. Another variable is the flux contained inside the tin lead or lead-free solder wire. Most of the solder alloys used for hand soldering have a core of liquid flux. Flux cored solder is like a tube that releases liquid flux. Flux has three main purposes. Once the flux is heated and activated, its primary job is to remove light oxides or contamination from the metal surfaces to be soldered. The metals to be soldered may look perfectly clean, but most metals will quickly oxidize whenever they are exposed to oxygen in the air. You might think of flux as a special kind of soap that removes oxidation or cleans metal so that it can bond properly. The second job of the flux is to prevent the freshly cleaned metals from being re-exposed to oxygen in the air in order to keep the surfaces from re-oxidizing. The liquid flux will cover or protect the freshly cleaned metal until the flux is displaced by the solder. The third job of the flux is to assist in the transfer of heat from the tip of the iron to the metals being soldered. The hand soldering operation usually happens very quickly, and it's impossible to see everything that's occurring since the parts are very small. So let's examine an animated hand soldering operation to observe how everything works. First, the tip of the iron is applied to the junction of the land and the lead to be soldered. This starts the heat flowing. Next, a heat bridge is formed by touching the solder wire to this same junction. This starts the flow of the flux and the initial melting of the solder. The flux moves away from the heat and ahead of the solder, over all of the metal surfaces. The heated flux removes oxidation or contamination from the metal surfaces. Everywhere the flux touches, it helps to heat up the metals. All of the metal surfaces need to be at the proper temperature or the solder won't bond properly. Now the solder wire is moved over to the opposite side of the land, while the solder and flux continue to melt. Liquid solder will move toward the heat. That's why you want the solder to flow from the opposite side of the heat source. Otherwise, you might not get enough solder to flow over onto the unheated side. The flux is pushed along by the solder as it performs its cleaning job. As it moves in front of the solder, it also floats away the loose contaminants. The flux and oxides will end up pooled around the edges of the land after the soldering operation is completed. Now the solder is chemically bonded or wetted to the land and lead just below the surface of the metals. Portions of the solder alloy, like tin, lead, or silver, mix with copper from the circuit board, forming a new type of metal in the area where they bond, which is called the intermetallic layer. Wetting is a term that's used to describe the adhesion of the solder to the base metal. Properly wetted solder typically feathers out to a smooth edge. Non-wetting is where the solder only wets to part of the land or the lead. The solder clumps like a ball to the top of the metal. We'll be talking a lot more about wetting later in this video, but for now, let's get back to the flux and learn more about the different types of fluxes that you may be using in various situations. The different types of fluxes used in soldering electrical connections are described in the IPC J Standard 004. The J Standard 004 separates all fluxes into one of three classes. These classes are based on the activity level of the flux, which essentially defines how strong of a cleaner they are and how corrosive they are to metal. Type L stands for low, type N indicates medium strength, and H is for high. In most cases, your company will select the type of flux you'll be using in order to be compatible with their cleaning systems. But it's important for you to understand that there is a reason to use only designated flux types and to follow your company's standard operating procedures for flux usage and cleaning. The next consideration is the amount or percentage of flux contained inside the solder wire. The percentage of flux is typically indicated on the label of the solder roll. Lead-free solder wire usually has a higher percentage of flux for a given diameter than tin lead solder wire. Generally speaking, once again, the higher the percentage of flux that a solder wire contains, the greater the cleaning action. But there will also be more residue to clean off the board. Flux residue can also be sticky. If these residues are not cleaned off the board right after the soldering operation, they can allow dust and other contaminants to stick to them. Some contaminants can be electrically conductive. If they are, this can create electrical leakage or even a short circuit. Flux cleaning techniques will be explained in section 4 of this video. Now let's discuss the size of the solder wire. Solder wire comes in different diameters, which is usually stamped on the end of the roll. Selection of the right diameter is an important part of the hand soldering process. For example, if you were to use a very thin solder wire for a large connection, it would take a long time to melt the right amount of solder. Keep in mind that after 3 seconds, you run the risk of overheating the solder or burning the circuit board. And if you were to use excessively large solder wire for a very small connection, you might not be able to control the amount of solder that ends up in the joint. Selecting the correct diameter is something you'll learn from experience. Our recommendation is to pick a diameter that is slightly less than half the size of the land that you'll be soldering. Now that you're familiar with soldering tools, solder types, and fluxes, let's discuss the nuts and bolts of how to hand solder through-hole components onto printed circuit boards. Regardless of whether you're using tin lead or lead-free solder, the hand soldering process should always begin by preparing or tinning the tip of the soldering iron. We explained earlier how oxidation forms on the surfaces of the metals to be soldered. This oxidation will also form on the tip of your soldering iron. Oxidation acts as a barrier or an insulator, which means that it can slow down the transfer of heat. An oxidized tip will prevent the rapid transfer of heat into the metals to be soldered. Lead-free solder is even more sensitive to an oxidized tip than tin lead solder. Notice the time difference between the properly tinned tip and an oxidized tip, melting a similar solder connection. To begin the tinning process, we'll take the hot soldering iron and wipe the tip 2 or 3 times across a damp sponge. This will remove impurities and oxidation, but it shouldn't cool the tip too much. If the tip is wiped excessively, or if the sponge is too wet, the tip could become too cold to use for soldering or tinning. Now let's apply some flux cord solder onto the tip. The flux inside the solder will flow first and chemically remove the oxides from the tip. Then the solder will flow over the tip and form a shiny coating. This tip is now properly tinned. Tinning is especially important on brand new soldering iron tips. Every time you install a new tip, it's important to tin it right away, or it may become untinnable and unusable. Tinning should be repeated as often as necessary. Whenever you can see that the tip is no longer clean and shiny, you've waited too long to retin. Heat can cause soldering iron tips to become so oxidized that they become unusable. It's a good practice to melt some solder onto the tip whenever you plan to let the iron sit for any length of time. This solder coating will keep oxygen from reaching the metal tip to protect it from severe oxidation. It's also a good practice to turn the iron off when it won't be used for an extended period. Some soldering stations will do this automatically. On some irons, oxidation can also form inside the barrel, which is the area between the tip and the heating element. If it's not removed, the oxidation in the barrel can also slow the transfer of heat to the tip and keep it from quickly reaching the soldering temperature. After we've prepared the tip of the soldering iron, we should be ready to start the soldering operation. We'll be using a temperature-controlled soldering iron with a chisel tip. The temperature of the tip will be set at 315 degrees C or 600 degrees F for tin lead solder, and about 350 degrees C or 662 degrees F for lead-free solder. Our tin lead solder will be 6337 eutectic with a 0.5 millimeter diameter. Lead-free solder will be SAC 305 with a 0.79 millimeter diameter. The flux in the core of the tin lead solder will be type L, or mildly activated. For lead-free, we'll be using type M, or medium activated flux. To demonstrate the basic technique, we'll be soldering a round component lead into a plated through hole. To hold the component in place, the leads are typically clinched at a 45-degree angle in the direction of the conductor trace. The leads are then cut off to a sufficient length to ensure visibility in the solder connection. Let's start with tin lead solder. Normally, this type of soldering operation would only take a few seconds to complete, but we'll be stopping the process in order to explain everything that happens as we go along. We begin by gently placing the cleaned and tin soldering iron tip against the lead and the land. This will transfer heat into both of these parts. Now the solder wire should quickly touch the tip of the iron to melt just enough solder and flux to form a heat bridge between the metals. Then we'll move the solder wire over to the opposite side of the joint, still touching both the lead and the land. When there's enough solder melted into the connection, touch the solder wire to the tip of the cut lead to cover the exposed basis metal. The solder wire is then removed, followed by the soldering iron tip. At this point, it's important to clean the connection if required. Then, we'll inspect the joint to make sure it looks right. A preferred or target connection is where all of the metals are covered by solder and the outline of the lead remains visible within the solder connection. Now we'll demonstrate the same soldering technique using lead-free solder. The main difference is that lead-free has a higher melting temperature than tin lead. So instead of a starting temperature of 315 degrees C, we'll set the temperature at 350 degrees C. Let's watch the soldering operation. Again, we clean the connection if required. The same inspection criteria will be used to determine a target solder joint. However, notice that the tin-silver-copper alloy is grainier in appearance than the tin-lead solder joint. This graininess is caused by the higher melting temperatures and is considered to be only a cosmetic issue. Let's review the soldering process once more to highlight some of the problems to avoid during hand soldering, regardless of whether you're using tin lead or lead-free solder. The tip should lightly contact both parts to be soldered. Pressing down firmly with the tip will not transfer the heat faster, but it may damage the land or the base material. Only a small amount of solder should be melted against the tip of the iron. If you melt all the solder by touching it directly to the tip, you may not get enough solder to flow onto the other side of the connection. Remember that solder flows toward the heat, flux flows away. Another problem is melting too much or too little solder into the connection. If you don't remove the solder wire at the right time, you could end up with something that looks like this. This time we remove the tip before the solder wire. Now we'll have to reheat the joint in order to remove the solder wire. Notice what happens when we reheat a tin lead solder joint? It doesn't look as smooth or as shiny as it was before. Now let's see what happens when you reheat the same solder joint using flux. In this case, the solder appears as smooth as it did before. Whenever you melt solder, you always need to add flux, either through the core of the solder wire or with an external applicator. Now let's look at the correct technique one more time. There is a lot happening in just a few seconds. The parts to be soldered are heated, cleaned by the flux, and joined together to form a physical and electrical connection. You probably noticed that we soldered on the solder source or secondary side of the board, away from the electronic components. This is done to minimize the amount of heat that reaches the components. If there is a particular component that is especially heat sensitive, a heat sink or thermal shunt should be used to help absorb the heat. This thermal shunt is attached to the lead to prevent excessive heat from damaging the component. On multi-layer boards that are extremely thick or have heavy internal ground or power planes, it may be necessary to preheat the entire assembly before hand soldering. Preheating brings the base material and the parts to be soldered up to a temperature closer to soldering temperature. This helps to make the soldering operation go a little faster, and it also reduces the temperature shock to the base material. Let's begin this next section with a discussion about removing or cleaning flux residues. Earlier in the video, we mentioned that flux residues can be both sticky and corrosive if they're not removed from the board. Before we discuss any flux cleaning techniques, it's important to note that there are special fluxes that are designed to be left on the board. The idea here is to eliminate the time and expense of the flux cleaning process and reduce the usage of various chemicals that can degrade our environment. IPC has a video devoted to the specific hand soldering techniques associated with these no-clean or low-residue fluxes. If you're using low-residue fluxes, you can skip this flux cleaning process. On fluxes that require cleaning, the general idea is to remove the flux residue right after the hand soldering operation by brushing the area with the appropriate cleaning solution. Your company will select the right cleaning fluids, which may be water-based or solvent-based, depending on the type of flux being used. This cleaning operation should always be performed immediately after the hand soldering operation. If it's not done right away, the flux residue will harden and become very difficult, if not impossible, to remove. An absorbent, lint-free, and ESD-safe tissue is often used to remove the solvent, so the residue doesn't just spread around the board. Even after this type of cleaning process, some of the flux may be trapped underneath the components, and some may remain as an invisible film. If a high level of cleanliness is required, additional machine cleaning will be necessary. There are water-based and solvent cleaning machines to re-clean the entire assembly. Again, your company will select a cleaning system that is compatible with your flux. There are some assemblies and specific component types that can be damaged by cleaning fluids. Your company will determine if the assembly is completely safe before sending it through any type of cleaner. Because each company sets its own procedures based on customer needs and the particular flux they use, there are many variations in cleaning methods, tools, and materials. In this final section, we'll be examining the qualities of tin lead and lead-free hand-soldered connections for through-hole components. Then, we'll look at some of the variations that may or may not be acceptable. Remember, earlier in the video we discussed the concept of wetting. Notice how the solder feathers smoothly onto the land and up onto the lead. The solder fillet is curved inward or concave. The solder covers all of the land and the lead. The texture is smooth and shiny for tin lead and may be grainy for lead-free. The outline of the lead is visible beneath the solder. The amount of solder here is just about perfect. These are good examples of target through-hole solder joints. Here's one now with a little less solder. You can see that the wetting is still good and the coverage is even. The fillet is concave. This solder joint is perfectly acceptable, even though there is less solder in the connection. Now here's another one with quite a bit more solder. The important thing to notice is the angle of contact between the solder and the metal. Proper wetting is indicated by a solder contact angle of less than 90 degrees, which is a square or right angle. The lower the contact angle, the better the wetting. As you can see, there is a range of acceptable solder joints. You will be expected to know an acceptable solder joint from a defective one before you begin soldering. Now let's look at some solder joints that are considerably less than ideal. This is a cold solder joint. Notice that the surface of the solder is dull and grainy. This is usually caused by insufficient heat. This is a disturbed joint. You can see that the solder shows stress lines, similar to the foothills in a mountain range. Movement during the cooling process can cause this condition. This is a fractured joint. The lead may have been moved after the solder solidified. Here we have a burned board. This was caused by contact with a hot soldering iron or too long a dwell time at the proper temperature. These are some additional examples of thermal damage. And this is a lifted land. Lifting can be caused by pushing or pressing down with a hot iron. Failure to allow cooling between heat applications can also result in a lifted land. Lifting can also indicate that the iron was left on the board for too long or that too high of a temperature was used. This joint has excessive solder. The fillet is not concave and there is solder flowing over the edge of the land. Excessive solder can also be detected when solder touches the component body or violates electrical clearance. This condition is called solder bridging. A bridge is an electrical path that was not intended. Here is a solder projection, also known as an icicle or a peak. These are typically caused by excessive solder or insufficient flux, and by the iron being too cool or being removed too quickly. These are solder balls. They can create electrical shorts by lodging in between conductors or component leads. Here's an example of non-wetting. The solder does not feather to a thin edge, and some of the base metal is partially exposed. Here's an example of de-wetting. Notice that all of the base metal is covered with solder, but there is an uneven fillet. The solder has receded in some places, leaving uneven mounds of solder. Another type of imperfection is the blowhole. These are usually caused by a gas escaping through the solder as it solidifies. If there is any moisture or solvent inside the hole or excess flux, this can create a blowhole as the gas expands and escapes. Although some of these conditions are always unacceptable, many of these imperfections could be allowed in various degrees, depending on what type of product they might be used in. For example, we'd all expect that any aircraft electronics would be highly reliable. but we may be able to live with some minor cosmetic imperfections in a consumer appliance as long as the product works. Tighter requirements generally means higher prices. For consumer products, where the idea is to keep the price down, the solder joints can tolerate a bit more variation from the ideal. The J Standard 001 has 3 classes of requirements, based on the final use of the end product. Class 1 is for general electronic products. Class 2 is for dedicated service electronic products. And Class 3 is for high-performance electronics, where failure is not an option. The specification and the class of requirements that your company uses to inspect solder joints will be clearly explained to you. Some companies build a wide range of products with different requirements. Other companies build only one class of product. Part of your job is to make sure to always apply the right criteria to each assembly. Although we've covered a lot of information in this program, a good through-hole solder joint is fairly simple to make. With knowledge and practice, you can become an expert.